Hello students, welcome to a live session with time. Now this is a chemistry session and we are going to continue with this chapter which we had taken up in the previous session, solutions, which is part of the 12th syllabus required for JEE main, required for NEET, required for any entrance exam. Solutions is a very important chapter. You learn lots of things in this. So in the previous session, let me give a brief on what we had done in the previous session. We had taken up three kinds of, or we said three parts of solutions. The first part was gas in liquid. Gases dissolved in liquids. And we found that there is a law which governs this solubility of gas in liquid, that is a Henry's law. Next we said we are going to take up a liquid solution. In a liquid solution, it's a binary liquid solution. We'll use the word binary here. So where only two components are there, a binary liquid solution where both the solute and the solvent are volatile. Both solute and the solvent are volatile, means they give vapor, means they contribute to the vapor pressure. So there is a vapor pressure from the solute and there is a vapor pressure from the solvent. That is a liquid. When it turns into vapor, both will contribute towards the vapor pressure, that is solute and solvent. So this is both volatile. The third one is where only one component is volatile. So that component we call it as a solvent. It's a binary solution where that solvent is volatile. Only the solvent is volatile, which means that we are dealing with a non-volatile solute. Non-volatile solute. We had already done this first one, Henry's law, and we have already started part of this liquid solution where both are volatile. And then we said that there is a Raoult's law which governs this solubility of liquid in liquid where both are volatile. Now, Henry's law and Raoult's law are actually specific cases from the Dalton's law. So the main idea is from the Dalton's law. We said the Dalton's law pertains to gas in gas. This is gas in liquid, Henry's law. Raoult's is liquid in liquid. So Dalton's law is a basis actually. The main idea is taken from the Dalton's law, where this partial pressure is total pressure multiplied by mole fraction. This formula or this form of the equation is common for all the three, whether it is Dalton's law or Raoult's law or Henry's law. Clear? So that we might have seen the mathematical form of both the laws. Clear? So this particular session, we will be continuing this too, right? So if this is the thing that we are going to do and what all we have done, we have mentioned, and what you're going to do is also being taken up, I think it is fair enough for you to know what exactly is going on, even if you have not attended the previous session. I hope this is clear. So let us start with a binary liquid solution, common characteristics. What are the common things that we find in a binary liquid solution? So usually A, we take it as a solvent and B is the solute. Usually, then what are all the characteristics for ideal as well as non-ideal solutions? Entropy of mixing, that is when you mix the two components A and B, you're going to have a positive entropy, means there is an increase in entropy because entropy depends on randomness. And when you mix solutions, there is more randomness. Entropy, you know, is also related to what is called mixed upness. Whenever you mix any two things, the entropy is going to rise. So entropy increases in this A meeting B, that is A mixing with B. And because the process is spontaneous, we know from thermodynamics that delta G is negative. So delta G is negative, standing for what? A spontaneous process. So it is a spontaneous process and it is a mixing process. So delta G mixing is negative, delta S mixing is positive. I hope this is clear. This is for any type of solution, irrespective of the type of solution, whether it is ideal or non-ideal. We happen to mention that in an ideal solution, A forces and B forces are similar to AB forces. So there is a uniformity of forces. That is what we said is in an ideal solution. An ideal gas has got no intermolecular force, but an ideal solution has got a uniformity of force. So uniformity of forces, uniformity of intermolecular forces, whether A interacts with A or B interacts with B or A interacts with B, it is similar, which means that A is not having any discomfort when another A is replaced by a B, or B is also not finding any discomfort when a B is replaced by an A. So ideal solution will have no change in the type of forces. The forces are all same. Clear? Now this is what we mentioned. All ideal solutions, they obey the Raoult's law at all concentrations and at all temperatures. I wanted to note down the examples under this because in the exam, entrance exam, they ask a question of this kind: identify the pair that forms an ideal solution. So we have taken up benzene, toluene, hexane, heptane, N-hexane, N-heptane. They are very similar. Molecules are very similar. Similarly, bromoethane, iodoethane, methanol, ethanol, chlorobenzene, bromobenzene, ethylene dibromide, propylene dibromide. They are all very similar. Therefore, there is a uniformity of force. Whenever there is a uniformity of force, we know that it obeys Raoult's law. That is what is an ideal solution. We have also seen the characteristics of ideal solutions, right? We'll again get to that. So in an ideal solution, the total pressure is the sum of the partial pressures. Delta H mixing is 0. Delta V mixing is 0, means there is no change in volume, there is no liberation of heat or absorption of heat whenever mixing happens, right? And we said that this is all possible because there is a uniformity of force. AA, BB is similar to AB. Clear? Yeah. If you have any questions, you can put it in the chat box, right? While you're watching the YouTube, you can put it in the chat box. From time to time, I'll just have a look at whatever questions you have put and I'll try and answer then and there. I hope the going is good. Yes. So we have taken up ideal solution. We have mentioned that ideal solution will obey Raoult's law. There is uniformity of forces. Enthalpy of mixing is 0. volume of mixing is 0. So they might ask in the entrance exam, identify which property pertains to an ideal solution. They might give volume of mixing is 0 or entropy of mixing is 0. Entropy of mixing cannot be 0 because whether it is ideal or non-ideal solution, the entropy of mixing is going to be positive, is it not? Now, this is what is the plot that you get between vapor pressure on the y-axis and mole fraction on the x-axis. The mole fraction of what? Mole fraction of B, starting from 0 going till 1. So as the xb starts from 0 to 1, when xb is 0, there is only xa. So it is pure liquid A. Pure liquid A will have this as the vapor pressure. Pa naught is the vapor pressure of pure liquid A. So on the extreme left of the y-axis, we find that this is only A, and therefore whatever vapor pressure you get is because of A, pure A. That is what is Pa naught. Now move on to this side. This side we have only B. So this is pure B. So this side, the right hand side y-axis is pure B. Left hand side y-axis is pure A. So pure B will have what? Pb naught as a vapor pressure, right? Now this is the Pa line. So as A falls from 1 to 0, just concentrate on that. As A falls from 1 to 0, the Pa naught will get down from Pa naught to 0. So this is touching the 0 part here. So as A turns 0 in quantity, the Pa also turns 0. So Pa naught becomes 0 there. But then what about B? B is going to rise. This is actually from 0. It rises from 0, right? Reaches Pb naught. This is the plot. Pa plus Pb is the total pressure. Sum of the partial pressures is the total pressure. Sum of the partial vapor pressures, right? So in the Raoult's law, we had written, I'll take a different color. So this is P equals Pa plus Pb. That Pa is nothing but P naught A into Xa, borrowing the idea from the Dalton's law. And Pb will be Pb naught into Xb. Now what I'm going to do is, we are going to remove this Xa, replace it with, see what is Xa plus Xb? There are only two components. And the sum of the mole fractions is equal to 1. So I can replace this Xa with 1 minus Xb. And the remaining I'll put as it is. So I have not got Xa now. I am proceeding with Xb. So I can write this as Xb into Pb naught minus Pa naught plus Pa naught is this P. Now what have we done here? We have plotted P versus Xb. So this is like y is equal to x into m plus c. Y is equal to mx plus c, which is a straight line, but it's what you got there, right? This is a straight line that you got. This is a straight line that you got. From this leads to that, correct? So P on the y-axis, that is a vapor pressure, and Xb on the x-axis, that is what you're plotting. Clear? You got a straight line. And the y-intercept, right, on the left is Pa naught, correct? Matching with this, right? If I am taking Xa, then I'll get Pb naught as intercept, and then I'll get this. I hope this is clear. Even those who are not from the mathematics background should be, fairly clear on this. So Pb we have written here, Pa we have written, Pa is Pa naught into Xa, Pb is Pb naught into Xb, clear? And this is for an ideal solution. So if you make P versus Xb, right, for various values of Xb, we'll find out that there is a straight line. We obtain a straight line. So we are obeying Raoult's law. So an ideal solution obeys Raoult's law. Clear? Now we'll take a real example, right? We have seen the examples here in the previous one. Benzene, toluene, hexane, N-heptane. So N-hexane, N-heptane plot we'll see now. Yeah, this is between heptane and hexane. So have we not got a straight line, right? With this as the PA naught of heptane, but that as the PA naught, that is P naught of hexane. So this is for heptane, that is for hexane, right? Clear? So this is the plot that you get. I think there is some mistake here. Heptane with a greater molecular weight should have less vapor pressure. Correct. More boiling point, less vapor pressure. Correct, it is. So this is at 40, close to 40, and that is at close to 100. Clear? So this is obeying Raoult's law. So this is like an ideal solution. Heptane and hexane, N-heptane and N-hexane. Clear? So now we'll move on to non-ideal solutions. So ideal solution, we have seen what are all the characteristics. We have checked what the plot can be, how the plot can be, what type of plot we get, right? It's a straight line we saw. And then we have also seen one example here of N-hexane and N-heptane. Now, let us work on a question, right? Let us solve this question. So ethylene chloride and then benzene. So let us take ethylene chloride as A. So PA naught is 236 and benzene as B, B for benzene, is 268 millimeters of mercury or torr. 1 mmHg is 1 torr. So we are required to find out what the total pressure. So P is equal to simple formula PA naught XA plus PB naught XB. PA naught value is there, given there. Now, how many moles of ethylene chloride do we have? 3 moles, and number of moles of benzene is 2. So what is the mole fraction? Mole fraction of ethylene chloride will be number of moles of ethylene chloride by the total number of moles. So I'll write here 236 into how many moles of ethylene chloride we have? 3. Out of how much? Out of 5. Is it not? Plus benzene's vapor pressure is 268 into 2 by 5. 2 moles of benzene out of 5 moles. Let us work out this. 3 6 are 6, 3 6 are 18, 3 3s are 9, 10, 3 2s are 6, 7. And then that one, 2 8s are 16, 2 6 are 12, 13, 2 2s are 4, 5. Add up. This is 14, 4, and then this is 12 divided by 5. So 5 2s are 10, 24, 5 4s are 20. Then I've got the answer. So A is the answer, correct? Even without looking at the remaining things, because it is 255, 504, 515. So this will give you 248.8. So we have got the answer even before looking at or even before doing a full calculation, right? So see to it that you don't do full calculation and yet get the correct answer, because that is very important. Getting the correct answer is very important. Saving time is equally, if not more, important. So you need to save the time so that you can spend time on more complicated questions. Hope this is clear. Yes. So we have solved one question, right, based on the Raoult's law for both the liquids volatile. Both are volatile. Clear? That is the second case. Now let us look at this. Liquid A and B form an ideal solution. These are all questions that have come in the JEE main. The vapor pressures of pure liquids A and B are given as 350 and 750 millimeters of mercury respectively at the same temperature. If XA and XB are the mole fractions of A and B in solution, while YA and YB are the mole fractions of Y and B in the vapor phase, what is the relationship now? Now, can we write PA as equal to PA naught into XA. Similarly, PB is PB naught into XB, correct? But what is YA? That is the mole fraction in the vapor phase, is PA by P. That is the partial pressure of this we can write as PA naught into XA divided by P. Similarly, I'll write YB equals PB naught into XB divided by P. What shall we do now? Divide one by the other. Left by left is equal to right by right. So P and P will cancel out, right? So YA by YB, we'll write here YA by YB equals, what is PA naught? PA naught is 350, PB naught is 750. So 350 divided by 750 into XA by XB, can we write? Now the answer is so clear. Now YA by YB is less than XA by XB, shall we say? Correct? Or shall we say XA by XB is more than YA by YB? Correct? Because this is less than 1. Is it not? So YA by YB is less than XA by XB, or XA by XB is more than YA by YB. So this is a different type of question. So I thought we'll take up as many different questions as possible so that you'll not face any problem when you're writing the entrance exam. So in the entrance exam, you will see to it that any question that comes was a question that you had already tried. Means similar type of question you had already come across. We have already revised, we have practiced questions on that kind too. So there is nothing new that is asked in the entrance exam. That should be our preparation. Our preparation should be such that we will not have a new question appearing in the entrance exam and then taking away a lot of time. So see to it that you practice as many different questions as possible so that when you are actually writing the entrance exam, right, it is something like it's a familiar thing. We have already done it. So we'll also be doing it and getting the correct answer. Now we'll move on to non-ideal solutions. Non-ideal solutions are those where we shall say that A forces and B forces, I'm talking about the positive deviation, right, is greater than AB. So what does this mean? That A is not comfortable with B because the forces are weaker. When the forces are weaker, A and B do not want to stay together. So how is what is the way in which A and B can stay away from each other because they are not interacting, right, to the extent that they interacted with themselves, A with A and B with B. So A wants to go more into the vapor because only in the vapor can A and B be away from each other, because in the liquid they are together, they need to be together. So A and B are prepared to move out more than what the Raoult's law asks. So there is a positive deviation from the Raoult's law. So when does a positive deviation from the Raoult's law happen? When you find that the AB forces are weaker. When the AB forces are weaker, A and B want to go out, go away from each other. And going away from each other means making more pressure, more vapor pressure, means more pressure than expected on the basis of Raoult's law. I hope this is clear. And for the negative deviation, what will happen? Just the reverse. So AB forces are stronger now. So A and B want to stay together because the forces are stronger. Therefore, they will go less into the vapor, or there will be a negative deviation from the Raoult's law. Hope this is clear, right? So there is a negative deviation from the Raoult's law because the AB forces are stronger. Whereas in the positive deviation, the AB forces are weaker. A and B wanted to go away from each other because their forces are weaker. Intermolecular forces between A and B are weaker. So we find that there are two types of non-ideal solutions where the AA forces and the BB forces are not equal to AB. When you say not equal, it means that it can be either greater or lesser. So if you find that AA and BB are stronger than AB, it means that A doesn't want to stay with B as much as it wants to stay with itself. So the vapor pressure increases, or there is a positive deviation from the Raoult's law. That is, you get more pressure than what Raoult's law predicts. So let us look at the plot, or first let us look at the example here. Positive deviation, because as we mentioned that in the exam they'll also ask, right? They'll give a pair of compounds and then ask whether it is showing positive deviation from Raoult's law or negative deviation. So positive deviation from Raoult's law is nothing but positive deviation from ideal behavior, is it not? So let us look at this. Different cases we have, right? Positive deviation where the AB forces are weaker. AB forces are weaker than AA and BB. Now let us look at the plot. Now this is the plot that you get. You're plotting what? Pressure versus the mole fraction, P versus XB, right? And this is between what? Benzene and carbon disulfide. So between benzene and carbon disulfide, the forces are weaker than between benzene and benzene, or between carbon disulfide and carbon disulfide. So we are having, so this is the dotted lines, the dashed lines are for the Raoult's law. So Raoult's law says that it should be here, but it is here. Means there is an increase in the vapor pressure, right? So this also increases, that also increases, leading to this increase. The P total will depend on the P of CS2 and the P of benzene. So P of benzene is also rising, P of CS2 is also rising, because both want to go more into the vapor, because they want to stay away from each other. Staying away means going more into the vapor. So benzene also goes more into the vapor. There is an increase here from the dotted line or the dashed line. Dashed line it is, not dotted line, dashed line. And carbon disulfide is also going to rise. And that together, that is P total is nothing but the sum of the partial pressures. So as the partial pressures rise, the P also rises. So there is a positive deviation from the Raoult's law. I hope this is clear. So let us move on to the, okay, a question to check whether we've understood it or not. Positive deviation from the Raoult's law. We know that acetone and carbon disulfide. Let us check. Here we have the last case here. Acetone plus carbon disulfide shows a positive deviation from the ideal behavior or Raoult's law. So answer is A. Clear? Now let us move on to the negative deviation, where we said that A, B forces are stronger. Every time we change the pen, right, there is either you're favoring the background or you're favoring the color on which the writing is. All right. So here there is one very, very important case, acetone and chloroform. This is a case where we have hydrogen bond involving carbon. For example, let us look at this. Acetone is CH3, C double bond O, and SCH3. Chloroform is HC, Cl, Cl, and HCl. Now hydrogen is attached to carbon here, but then carbon is attached to electron withdrawing Cl, Cl, and Cl. So carbon has become so much positive that it takes away the electron density from the CH bond, making hydrogen positive. A positive hydrogen will interact with the negative oxygen, and that is what is a hydrogen bond. So this is a special case where a hydrogen bond is formed by having a hydrogen not attached to fluorine or oxygen or nitrogen, but attached to carbon. Usually it doesn't happen, but this is a special case, right? That is why this is a very, very important case that we are talking about. Acetone and chloroform will form a hydrogen bond which is not a usual hydrogen bond. Hydrogen bond happens only when hydrogen is attached to electronegative atoms such as fluorine, oxygen, nitrogen, but not when it is attached to a less electronegative carbon. But here it happens. So there's a special case there. Hope this is clear. Yes. So let us move on. We have this as a basis. This is a Raoult's law expected thing, but then there is a fall. Raoult's law expected thing, but then there is a fall. Raoult's law expected thing for the P total, false. So here acetone has a vapor pressure falling. Chloroform has a vapor pressure falling, and therefore the entire solution will have a P total less than what is expected on the basis of Raoult's law. I hope this is clear. So this is acetone interacting with chloroform, right, through a hydrogen bond. So AB forces are stronger now. Between acetone and acetone, we have dipole-dipole force. Between chloroform and chloroform, also we have dipole-dipole force. But between acetone and chloroform, we have got hydrogen bond, and hydrogen bond is much stronger than a dipole-dipole force. Hope this is clear. Yes. Now let us check how much we have understood. A solution of two miscible liquids showing negative deviation from the Raoult's law. Negative deviation means what? There is a decreased vapor pressure, and therefore there is an increased boiling point. Where is this? Decreased vapor pressure and an increased boiling point. Decreased vapor pressure will never lead to decreased boiling point. Increased vapor pressure can lead to decreased, but A and C are conceptually wrong. When the vapor pressure increases, the boiling point has to decrease. Or when the vapor pressure decreases, the boiling point has to rise. Let us check just two liquids, right, reaching 1 atmosphere, right? Let us say that this is liquid A and this is liquid B. And this is vapor pressure. Now, which of these two liquids requires more heating to reach 1 atmosphere? Is it A or is it B? A is closer to 1 atmosphere. Its vapor pressure is close to 1 atmosphere. So there should be lesser heating. Lesser heating required. Lesser heating required means less boiling point. So vapor pressure is higher, the boiling point will be lesser. Correct? That is what we find here. So whenever you have a negative deviation from Raoult's law, it means that AB forces are stronger. A and B do not want to go more into the vapor as demanded by the Raoult's law. They'll go less, and therefore less means negative deviation. And this is less because the two liquids are having greater intermolecular forces, and therefore there is an increased boiling point. So decreased vapor pressure, increased boiling point will happen for a negative deviation from the Raoult's law. Negative deviation means vapor pressure is less. Less means decreased. And when the vapor pressure falls, the boiling point rises. Now, this is a summary of what all things we have read so far. So you can make a note of this, except for the last one. Last one we have not discussed yet, azeotropes, right? The remaining ones are all known to you now. So far, we have done sufficiently to know what Raoult's law means, what an ideal solution means, what a non-ideal solution with a positive deviation means, what a non-ideal solution with a negative deviation means, right? What will be the volume of mixing? What will be the enthalpy of mixing? Let us look at this once again. So if it is a negative deviation, right, there is an exothermicity. Heat is released, and there is a decrease in the volume because AB forces are stronger. Whereas the opposite happens in a positive deviation. The volume increases and there is endothermicity. This is endo and this is exo. Clear? Delta G mixing is always negative. We said in the very first slide that we saw that delta G mixing, whether it is for an ideal solution or for a non-ideal solution, is always negative because the process is spontaneous. And then we said that there is increased mixed upness or randomness, and therefore entropy of mixing is always positive. There is no change, whether it is ideal or non-ideal, non-ideal of any kind, right? Delta S mixing is always positive, delta G mixing is always negative. Now we'll move on to azeotrope formation. Azeotrope happens whenever there is a large deviation from the Raoult's law. We can deviate from the Raoult's law either negatively or positively. That is what we have seen, is it not? Negative also we can, positive also we can. So let us look at what is an azeotrope. An azeotrope is whenever a binary liquid solution on heating distills over completely without change in composition. So what does this mean? That you have a liquid, let us say that you have we'll have a flask, let us say round bottom flask, wherein you have got both the liquids A and B, right? Suppose A is more volatile than B, then we'll have more A going out than B. So B will go less, A will go more. And then when you condense, there will be more A in the condensate because A has gone more, B has gone less. But here what is happening? A and B are not going to different extents. There is no change in composition, which means that the liquid composition and the vapor composition are the same. So we are not able to separate the mixture at a particular composition. This happens at a particular composition. So at a particular composition, the liquid and the vapor will have the same composition, means there is no change, right? You will not find more A in the vapor or less B in the vapor. As much A and B were there in the liquid, so much will be there in the vapor. That is what you are saying, distills over completely without change in composition. So it is as if it is behaving as a single liquid, as if you do not have a mixture of liquids. When you have a mixture of liquids, there will be different tendencies to go into the vapor, but then this is behaving as a single liquid. But behaving as a single liquid happens at a particular mole fraction. It will not happen at all mole fractions. It will happen at a particular mole fraction. And that particular mixture, which does not distill with a change in composition, is called an azeotropic mixture. An azeotropic mixture, as we said, can come either from a positive deviation from the Raoult's law or from a negative deviation from the Raoult's law. So when you have a positive deviation from the Raoult's law, it will be a low boiling azeotrope. There is a boiling point will become less. Low boiling azeotrope. And when there is a negative deviation from the Raoult's law, we have a high boiling azeotrope. Kindly note, make a note of that. So whenever the vapor pressure is less, the boiling point is more. Wherever the vapor pressure is more, the boiling point is less. Clear? So azeotrope happens only when there is an extreme deviation from the Raoult's law, whether positive or negative. And the liquid solution behaves as a single liquid and it cannot be separated upon distillation. No separation possible upon distillation. So whenever azeotrope forms, right, it's a difficulty because separation cannot happen with distillation. Now, as we said, when you have a positive deviation, we have a minimum boiling azeotrope. That is, water and ethyl alcohol is a well-known example where an azeotrope is formed when we have 95.5% of alcohol and the remaining percent of water by volume. And then let us look at that. This is a minimum boiling azeotrope. Maximum vapor pressure, therefore minimum boiling point. Look at this. At this part, that is, what was the thing we mentioned? Here, right? We'll use a different pen. Yeah. Now look at this. This is 95% ethanol. The remaining is water, right? And you know that water boils at 100 degrees Celsius. Ethanol boils at 78.5. But then this azeotrope boils at a lesser temperature. That is why it is a low boiling azeotrope, which boils lesser than the pure components, lesser than ethanol, lesser than water. Clear? So this is low boiling azeotrope because there is a positive deviation from the Raoult's law. I want you to check the examples that we had given under positive deviation from the Raoult's law, where we found that ethyl alcohol and water having positive deviation from Raoult's law was part of the example there. So the same example is now here as a low boiling azeotrope. So extreme deviation, extreme positive deviation from Raoult's law leads to what? Formation of a low boiling azeotrope. Next, for the negative deviation from the ideal behavior, we have a maximum boiling azeotrope. And look at this. Nitric acid and water will boil at 393.5 Kelvin, which is more than the boiling point of HNO3, more than the boiling point of water. Water boils at what? 373 Kelvin, is not in the Kelvin scale. In fact, any acid, any mineral acid and water combination will always form a negative deviation, will always give a negative deviation from Raoult's law or a maximum boiling azeotrope. Now look at this. Here the boiling point is 120.5, more than the boiling point of nitric acid, 100% nitric acid, more than the boiling point of water, 100% water. So here we have a azeotrope formed. Here is the azeotrope formed. Draw a perpendicular from there, and that is a composition where the azeotrope is formed. I hope this is clear. So nitric acid versus water. So we have done azeotropes with Raoult's law as a basis. More deviation from the Raoult's law will result in the formation of an azeotrope. Now there are other examples, right? Minimum boiling azeotropes. What do we have? Carbon tetrachloride, ethyl alcohol, methanol and acetone, ethyl acetate, and then water. Similarly, for maximum boiling, we have water HCl, chloroform acetone, we have seen. HBr is also mineral acid and water. Azeotropic mixture cannot be separated into pure components by fractional distillation, or distillation cannot result in a change in composition, and we cannot do a separation. There are other methods, techniques, where the two liquids can be separated by adding a third component, for example. Right? If it is a binary, you cannot do it, but you can add a third component, and you can do some other processes, right, which can lead to separation. Clear? Let me check if you people have got any questions, right? If there are no questions, it can mean two things. One is you've understood it properly, right? Or second, which should not happen, which means when a student is not attentive, no questions, no doubts, because no understanding, no tendency to listen. So there are two things. Second thing should not happen. First thing, if it happens, we are always there to explain once again. Now, on to testing our knowledge. Which of the following binary mixture doesn't show the behavior of minimum boiling azeotropes? Which means that you're looking for a maximum boiling azeotrope. Look at this. This is an acid. A phenol is an acid, and aniline is a base. And acid base can interact well. So this should be the example where we will not have minimum boiling azeotropes. The AB forces are stronger because there is an acid base interaction. It should be stronger. So stronger interaction will see to it that you have negative deviation from the Raoult's law. Negative deviation from the Raoult's law sees to it that you get a high boiling azeotrope, high boiling or maximum boiling azeotrope. So we want no minimum boiling azeotrope. We want only a maximum boiling azeotrope or a high boiling azeotrope. And that should be when AB forces are stronger, which will happen in the case of B, where there is an acid phenol interacting with the base aniline. I hope this is clear. Yes, this we have seen is a positive deviation from the Raoult's law, is it not? Acetone CH2, repeated. Similarly, methanol and chloroform. Similarly, water and ethyl acetate. We have seen in the previous cases. Is it not? These are all coming as minimum boiling. Now, let us check if you are able to solve this. A solution of chloroform and acetone is going to give a maximum boiling azeotrope. Yes, that is what you have seen already. A solution of ethanol and water will give a minimum boiling azeotrope. A solution of benzene and toluene is an ideal solution. Therefore, volume of mixing is 0. Therefore, a solution of acetic acid in benzene will dimerize. We know that acetic acid can dimerize in benzene, right? Like this. You can have CH3. Acetic acid is what? CH3COOH. A C double bond over there and OH here. The same acetic acid which ionized in water, because it's functioning as a weak acid, right? It's a carboxylic acid. Carboxylic acid will undergo ionization. That happens in water. So in water, acetic acid will ionize or will give what? Dissociation. But here it is forming a dimer coming under association. So acetic acid can associate in benzene, dissociate in water. So in association, what do we have? We have got 2 hydrogen bonds formed and 2 molecules have participated. Therefore, they form a dimer. Dimer means 2 parts joined together, which will behave as a single part now. I hope this is clear. So where is this option? A3, B1 is option A. C4 it is, and then D2. Clear? We'll move on to. All right. So I thought we will be left with less time so that we'll say goodbye, right? Goodbye after this second part. Now, I think there is sufficient time for us to take up the third part as well. But then before we take this at the end, we can take a small break and then make a note of the channel that we are into, right? What all interesting videos you can find in this, right? We can also find short videos or live sessions, right? All these things are available, right? And if you want to make time as a part of your successful journey, right? You can visit us, you can contact us, right? For classroom coaching or for any online courses, right? All the details are available here. So before we say thank you, we are here with the third part that we talked about, where we said that only one component is volatile. So here I'll say that A is volatile solvent it is, and B is non-volatile. B doesn't give any vapor pressure. B is a non-volatile solute. So properties, that is colligative properties, are what? Which depend only on the number of solute particles, not on the nature. Suppose you have 3 chloroform molecules or 3 sucrose molecules, right? Or 3 million sucrose molecules or 3 million glucose molecules, they'll have the same colligative property, because colligative property depends on what? Only the number of the solute particles. Solute particles could be anything, right? Could be any solute. It need not be belonging to only an organic substance or any substance for that matter. It only depends on the number, not on the nature, not on the type of bonding that the solute has. Clear? Now, these are in a given volume of the solvent, right? The solvent is fixed. Those properties are called colligative properties. Colligative means collection. Collection of what? Solute particles. So when the collection is the same, the properties are also the same, also having the same values. Now, colligative properties depend on the nature of the solvent, right? We said they don't depend on the nature of the solute. They depend on the number of the solute, but then they depend on the nature of the solvent and are given only by dilute solution. So whenever you have a colligative property, we'll find them only in dilute solutions, and when there is a non-volatile solute. This is very, very important. Non-volatile solute and a dilute solution, right, can give us colligative properties. What are these colligative properties? They could be a lowering of vapor pressure, or an elevation in the boiling point, or a depression in the freezing point, or simply osmotic pressure. Osmotic pressure is the absolute value. No decrease or no increase. There is a decrease in the vapor pressure. There is an increase in the boiling point. There is a decrease in the freezing point, but this is osmotic pressure. Osmotic pressure by itself, right? The absolute value, not a difference, is a colligative property. So among the colligative properties, what are all the things that we have? Probably will not be able to, there are only a few more minutes left. So I'll be concentrating on these properties, how they are all related to each other. So let us look at that part. Now, we took the Raoult's law as P equals PA naught XA plus PB naught XB. Right? This was for both volatile. Both the components volatile. It was a solute and a solvent. But now we will not have this. This is no longer there. So whatever is the total pressure, that is the partial pressure of A, which is equal to PA naught into XA. So this Raoult's law has converted to this when only one component is volatile. What is that component? That component is A, because only A gives the vapor pressure. B doesn't give. Clear? So the Raoult's law, I am putting it in this form now. So PA equals PA naught into XA. Can we not write XA as 1 minus XB? We can. Or 1 minus XB equals PA by PA naught. Even for those who are from the non-mathematics background, this should not be a problem. I'll bring this PA by P naught this side, PA naught, and then send the XB to the other side. So this will be PA by PA naught here, and that will be XB there. So we can say that PA naught minus PA by PA naught is equal to XB. So this is the Raoult's law for the second case where only one component is volatile, which means that B is a non-volatile solute. So whenever there is B as a non-volatile solute, we will not have the PB component. So PB component is removed. So whatever is the total pressure, that is nothing but the partial vapor pressure of A, because only A is going to give the vapor. So if I had only A in the container, all the molecules on the surface belong to A, is it not? And suppose I have a lid here. The molecules which are having greater energy, greater kinetic energy, they can come out of this liquid and get into the vapor, right? And form vapor, and we'll get a vapor pressure at equilibrium. So vapor pressure is the equilibrium value of, let us say, A, right? And whatever is the vapor pressure of only A, that is PA naught. Now what have we done? We have added a non-volatile solute B. So few molecules on the surface are also belonging to B. So the number of molecules of A available on the surface is less. Less because you have added B. How much you have added B? As much you have added B, so much of A will be less on the surface. So the PA naught will come down to PA because you have added B. Because you have added B, B is also forming part of the surface, and the molecules from the surface going into the vapor have become less. Therefore, whenever you added a non-volatile solute, the PA naught is decreased to PA. So there is a lowering of vapor pressure. So PA naught minus PA is the lowering of vapor pressure here. And that lowering of vapor pressure is a colligative property because it depends on the number of moles of solute. Clear? And this entire thing, PA naught minus PA by PA naught, something like selling price minus cost price by cost price, right, is the relative lowering of vapor pressure. That whole thing. PA naught minus PA by PA naught is relative lowering of vapor pressure. So the Raoult's law now says that for the second case, relative lowering of vapor pressure is equal to mole fraction of the solute. This is clear? Yes. So this is what we get from the Raoult's law, right? Converting this part, this is the Raoult's law in its full form. But then you're having this now. A is volatile, B is not volatile. When that happens, this is what we get. So this is also Raoult's law. This is Raoult's law for a case where only one component is volatile. That is, A is volatile, B is non-volatile. Then we derive this kind of Raoult's law equation for this case, right? Later you'll find that there is an elevation in the boiling point, right, which depends on the lowering of vapor pressure. And lowering of vapor pressure, as you have seen, I'll put that once again, delta P by PA naught. So PA naught minus PA, I'm writing it as delta P is equal to XB we wrote. XB is NB by Na plus NB. Small amount of simplification will do. It's a dilute solution. If it's a dilute solution, what is going to happen? This NB will be much less when compared to Na, so this can be neglected. So I can write this as almost same as NB by Na. NB is nothing but the weight of B by molecular weight of B multiplied by Ma by Wa, right? If I multiply with 1000 and divide with 1000, what am I going to get? Let us look at that. This part is nothing but molality, correct? There is molality. So delta P by PA naught is equal to molality, which is the weight of the solvent by molecular weight of the solvent into 1000 by Wa, which is, weight of the solute, weight of the solute by weight of molecular weight of the solute into 1000 by weight of the solvent. That is nothing but molality. Into what? Into Ma divided by 1000. I can send this PA naught to the other side. So I'll write delta P as equal to M into Ma by 1000 into PA naught. For a given solvent at a particular temperature, this entire thing is constant. So delta P is proportional to M, which I'm going to put it here. So delta TB is also proportional to M. Here. That is how we get delta TB as equal to proportionality constant Kb into M, where Kb is also called the molar elevation constant. Clear? So this is how we get the elevation in the boiling point from the lowering of the vapor pressure. A similar equation you also get for the depression in the freezing point. Delta TF is equal to some Kf into M. Right? This is how we derive the elevation in boiling point and the depression in freezing point from the lowering of vapor pressure. I hope this is clear. Let me check if anyone is having any doubts. All right. So quickly, just 1 minute. This is pure liquid A. I'll have to change the This is pure liquid A, and this is A plus B. Here, all the molecules of the surface, on the surface, were made up of A. Here, some B molecules are also there. And therefore, the tendency to go into the vapor has become less. How many A molecules were here? 1, 2, 3, 4, 5, 6. Here only 3, which means that there is a lowering of vapor pressure because of addition of a non-volatile solute. So here it is written that this orange one is the non-volatile solute and this bluish green is the volatile solvent, that is A. Here. Now, this is the boiling point of the liquid, that is pure liquid, and boiling point of the solution. So there is an elevation in the boiling point because there is a lowering of vapor pressure. Similarly, there is a decrease in the freezing point of the solvent, freezing point of the solution. So it is coming down. So there is an elevation in the boiling point because of the decrease in the vapor pressure, and that is followed by decrease in the freezing point. Clear? So one diagram for all the three. And the final one is osmotic pressure, where you have a semi-permeable membrane, right? And only the solvent is able to move. So with this, probably we'll put an end to this session, because more we cannot take up, especially when there is, a requirement of greater time for completion. So till this, we will, make it as a concluding thing. And then in the coming session, we'll take up the remaining parts, right? Remaining part along with questions. And that should be signaling the end of the solutions. So shall we end this session? Right? I hope this session was useful, right? I have seen that you have noted all the details of our channel and the website, and we hope that you'll get in touch with us and then make us part of your successful journey. Thank you.